Unit 5 in AP Physics is a unit all about rotation, and we're going to start our study of rotation with the study of objects that are moving with a fixed axis. So in other words, the center of the rotation remains in place. In order to study this motion, we're going to start out with the same way that we started out the study of linear motion with kinematics. There's a lot of similarities between linear kinematics and angular kinematics. So let's start by looking at those quantities that we've studied. For example, we started out with an object's position. We used either the x, the y, or the z variables to represent where it is located, or maybe even an r vector that included all three directions. With angular motion, we use the angular position of an object, and we use the symbol theta to represent that angular position. Next, we learned about displacement, or the change in the position of an object. We could have a displacement in the x direction, a displacement in the y direction, a displacement in the z direction, or in general, we use r as our vector to denote three-dimensional displacement. In angular motion, it's still the change in the angular position, otherwise known as that angular displacement or delta theta. Next, we learned about velocity. We talked about how we could have an average velocity or an instantaneous velocity, and we use the symbol v. With angular motion, once again, we can have an average or an instantaneous, and we use the symbol omega. While it looks a lot like a W, it is a Greek letter called omega. Lastly, we learned about acceleration, about average acceleration and instantaneous acceleration. We use the symbol A for acceleration with linear motion. And similarly, we can have an angular acceleration, and we use the symbol alpha. Again, that's the Greek letter alpha for angular acceleration. Now, you may have noticed that all of these quantities have vector symbols on top of them. But the way that we do direction with angular motion is a little bit different. Specifically, when we're doing direction with angular motion, we are using something called the right-hand rule. So here's a diagram that showcases the right-hand rule that we'll use. You could probably guess by the name of the rule that we're using our right hand to do this. And in this case, we're going to kind of give that thumbs up signal. We're going to rotate our fingers the direction that an object is rotating in, or possibly the direction that an object is accelerating. And our thumb points the direction of the, gives us the direction of that vector. So for example, in what you see on this diagram here, if my object is like, let's say a record that is playing, and if I'm looking top down, let's say that it's rotating counterclockwise. So I would rotate my fingers counterclockwise, and my thumb would be pointing straight up. So the direction of that angular velocity would be in the positive z direction. Now, after learning the names of those quantities with regular or linear kinematics, we talked about some calculations that we could make. We can do similar calculations with angular quantities. So, for example, we know that we can do average velocity by doing the displacement divided by time, or instantaneous velocity with doing the derivative of the position function. It's the exact same thing for angular quantities. The average angular velocity would be the angular displacement divided by time, or my instantaneous angular velocity is the derivative of the angular position function. Acceleration is similar. I could do average angular acceleration by doing the linear acceleration by doing the change in linear velocity divided by time, or we know that linear acceleration is the time derivative of the velocity function. And it's the exact same way with angular quantities. Then we moved into some kinematics equations that we talked about being able to use when we have a constant acceleration. Here's one example. The final velocity equals the initial velocity plus acceleration times time. Now, I've left off the vector symbols out of this equation to mimic what you see on your equation sheet. We have that exact same kinematics equation for angular motion as well. The final angular velocity equals the initial angular velocity plus the angular acceleration times time. Here's one other equation that we see on our equation sheet in both linear and angular formats. Once again, you'll notice that there aren't vector symbols on top of either the linear or angular equations. To be honest, I'm not real sure why the equation sheet leaves them off there, because really there should be vector quantities on top of these symbols, since we do use positives and negatives for direction. I'll also point out that on the equation sheet there is one additional equation for linear kinematics, but for the angular quantities it only contains these two kinematics equations. But it's pretty easy to take that third equation and figure out what it would be if we were doing angular motion.